All right, before I hand it over to Johan for his LDC talk, there's another announcement I'd like to make. Thanks to Maria, we now have an Instagram account that we didn't have before, dlang.org, no dot, just dlang.org is our handle. Some of you have already been posting pictures on Instagram. If you post pictures with a hashtag DConf or hashtag dlang or direct message us a picture, we will post it on our new dlang.org account. All right, so send us your pictures, please. All right, Johan?
All right, good morning, everybody. We just had a very nice talk on the higher levels of programming, higher levels of abstraction. This is an LDC talk, which means it's about compilers, and specifically what I work on, the part of the compiler, is really the lower assembly, very close to the machine parts of the compiler, right? So I hope you can live with the switch. I've titled the talk LLVM-backed goodies in LDC, and basically what I'd like to tell you is how we use LLVM, or maybe, who's familiar with LLVM, by the way? Okay, so maybe half of you, maybe a bit more. Good. So explain you briefly what is LLVM or how we use it, and then show that with two examples that I think show very well how the capabilities of LLVM, and more specifically maybe the capabilities that you're not so familiar with. And as the slide says, please feel free to interrupt me anytime for questions or comments. I'd rather have it interactive than have all the questions at the end. Okay, so in summary, this is what, if you run LDC, the program that you're running is a mix of three big components. One is the DMD front end, that's doing the semantic checking of the D. Basically, the DMD front end knows the D language. LDC doesn't know too much about D. What it gets from the DMD front end is something called an abstract syntax tree, so the AST. You follow the arrow here. This is your source file. It goes through the DMD front end, and then what the DMD front end outputs is an abstract syntax tree. That one goes to LDC. That's the core of LDC, modifying or translating the D language AST, the abstract syntax tree, to LLVM language, what is called LLVM intermediate representation, LLVM IR over there. And that then goes to LLVM, which takes care of generating the actual optimization and generating the machine instructions for the CPU that you're targeting. So LLVM will output object files, CPU instructions, or LLVM code itself. That's also a possibility. So these big three components, actually LDC is the smallest of the three. Right? The syntax checking, the type checking, template instantiation, all of that happens in the front end. Then LDC is more of a glue layer between the front end and the back end LLVM. And LLVM is a very big, takes an hour to compile or even longer. It's a very big project and has lots of functionality. So what does LLVM provide? LLVM provides, of course, machine code generation for different targets. Actually, the LDC compiler is already a cross compiler for anything that you added to the build of LLVM that you're using. So it's x86, maybe ARM, PowerPC, whatever, and even GPU and OpenCL. And unfortunately, Nick yesterday couldn't show what that looks like, how to program for a GPU using dcompute. Sorry, Nick, I won't show it here either. But there's a link here. Please go and find that on GitHub. It's pretty awesome. It looks like decode, and you can run it on your GPU. And it's basically enabled by the capabilities of LLVM. Of course, then, I think what you're most familiar with is the optimization that LLVM provides. It has a very strong optimizer, and it's generating. If you write an algorithm, most performance you get by changing the actual algorithm, right? But then if you compile it with DMD, the performance difference between DMD and LDC is because of the optimization that LLVM provides, full stop. The other thing that you may not realize is that because we use LLVM, we have a very well-defined interface to compile decode too. LLVM IR is very well specified, and it's very precise. It has good precise semantics of what each operation should do. And in fact, this also makes it easy for us to test the compiler. Right? We can look at the output that the LLVM IR that we output, that LDC outputs, and can check whether this makes sense, right? Like, is the linking of a symbol, is that correct? And are the operations that we're doing, are they correct before we generate machine code? Of course, you can execute the program and check that the program executes correctly, but it doesn't mean that the code was actually correct, especially when you link in other things. You want to make sure that the LLVM IR is correct, rather than the simple program that you're testing. Other things that you may not be so familiar with are sanitizers. Who's familiar with the sanitizers of Clang or GCCS as well? Okay, less than half of you. This talk will show you two sanitizers, AddressSanitizer and fuzzing. And also, closely related is the profiling capabilities of LLVM. John Degenhardt gave a talk 2 days ago about PGO and LTO. That means profile guided optimization and link time optimization. Here I'll discuss the innards, how PGO works. Other things that are fairly recent in LDC is the JIT capabilities of LLVM, so just-in-time compilation. So look into this UDA. You can attach it to a function, @dynamic_compile. What that does is it basically enables the program to, at runtime, compile your function or recompile it for where then at the point where you recompile it, it may know the values of some global variables and can optimize your code for it. Right? I haven't seen people use it so much, but I think it's very powerful in performance critical applications. Right?
What does this imply on the runtime?
Okay, it basically implies you have to carry LLVM with it, right? What it does in summary, it emits the function as LLVM IR in the executable, and then you need the LLVM optimizer and the JIT runtime to actually be able to compile that LLVM IR to machine code at runtime, yeah. So it definitely will make your executable much bigger. Just one more there. Okay, yeah, I'd rather not dwell on it for too long. But it's definitely something cool to look into. The other thing is it provides a linker as a library, as it does the Clang compiler is also a library, which is also already used for a long time in Calypso, and recently Attila used it in being able to just, you type include a C++ header, which calls the Clang library to interpret that piece of C++ code, which you can then use in your decompiler again. The linker as a library enables us to integrate a linker into LDC so that you have a cross-linker even, because the linker that LLVM provides is also a cross-linker. But that's I think it works on some platforms and it doesn't work too well on other platforms just yet. All right, and there's much more that LLVM provides. Okay, I think it's the first time on DConf that I show some LLVM IR. Last year I showed assembly code, and I think actually LLVM IR is much easier to read. And in order to explain how certain things work in LDC, looking at LLVM IR I think helps a lot. So here, I'll show two short examples of how decode looks like in LLVM. So if you look at the snippet on the left, we define two functions, and then we have a function here, call bar if foo is equal to 42. Simple function, there's an if statement, calls foo, checks if it's 42. If so, it returns the return value of bar, otherwise it returns false. In LLVM IR, it looks like this on the right-hand side. We define a function called call bar if foo is equal to 42. It returns an I1, an integer of 1 bit, which is a Boolean. it takes no parameters, and then there's this #1, which basically is like a UDA, or it's a set of attributes that this function carries. Then first statement, we call foo, and foo apparently is a function that returns an integer of 32 bits. And we assign it to this %1 thing. %1 is a local variable, and LLVM-IR is a single assignment language. Shahar, yeah?
Does that mean the IR is already platform dependent? Because things like int can be platform dependent.
Yes, it's, I would say, mostly platform independent, but it's definitely platform dependent. Things like ABI, like how you pass things to a function, that depending on your platform, the IR looks different. Integer though, in D, an integer is always 32 bits.
In D, yes, but,
And
if that's the IR, then obviously the front end has to resolve that.
Yes, and so also the platform may not even have 32-bit math, right? So this is not, it's called legalization. Just as an example of platform independentness, you can create an integer. It says 32 here. You can create an integer of 128 bits, but your platform may not support that, and so there's a legalization step where it changes code so that it can deal with such things. Yeah. So it's not completely platform independent, but it mostly is. Where was I? Okay, yeah, so it's a single assignment language, meaning that this %1 is a local variable, but you can only assign to it once. That's very important to know about LLVM-IR, and it kind of makes reasoning about the IR also much easier. It's like everything is immutable, if you want. Then there's a comparison here, integer comparison. Is this thing equal to 42? The result is stored in %2. Then we branch off of this Boolean value, either to label if or the label end if. If we branch to label if this thing was true, then we have to call bar, and then we return the result of bar. Otherwise, there's this dummy thing, which is a quirk of how LDC emits LLVM-IR. Right? This is non-optimized IR at this point. And it just helps us generating this kind of code. But if this thing was false, it would jump to label end if, which is here, and it returns false. Is that clear? Simple example. A more complex...
If you go back to the... Why do you need the after return label?
Since
you're not actually
I think it's
jumping
actually it's because we have a scope here in if.
Okay.
And in this scope we do a return. But the scope is not done yet, right?
Yeah.
And that's why we have this label afterwards. It's a quirk in how we generate the LLVM-IR. It's definitely not needed. Once you run the first optimization step, it's killed, right? It's dead code. There's no predecessor for that basic block, and it will just be elided immediately. I left it in to show you that the LLVM-IR that LDC outputs is generally not optimal at all. It's just for ease of generating it, and then you run the optimizer to get better code. The code here is optimized, by the way, otherwise it would be too much.
Yeah, I just want to expand a little on that. The way the basic block system in LLVM works is that if you specify you want to jump to somewhere, it has to be already a basic block. So you have to know where you jump to at the point you want to say that there's a jump here. And to be able to make that work, if you don't know what you're going to jump to, you have to use two jumps and therefore creating two basic blocks to have a fixed label, and then you can fix the rest up after the function is done and you know all the jumps. It's really annoying about LLVM-IR, but that's why these...
Yeah, although I
don't
think
do
it's
anything
mostly, it depends how you treat these things in your own program, right? There's other ways of generating the error. So, in any case, Let's continue. Here I've showed an example of a virtual function call, or what a class looks like with a virtual function call. And so we have a class A, has one field, integer, and then has one function foo. And then there's a global function here that's called call foo, takes an A as parameter, and then returns a.foo times 1, 2, 3. Okay? So this is a virtual function call here, right there. First, in IR, we have to define the type class A, which is in the module DConf. It's a type, and it starts with a pointer to an array of 8-bit pointers, or pointers to 8 bits, which is a void pointer. Then there's another pointer, a void pointer, which is the infamous monitor field. This is the V table here, this is the monitor field, and that's your field, int field, the 32 bits. Okay? We have to define a initialization value for this thing, which is basically the thing that all A's get initialized to in the beginning, right? Which is the V table here. The monitor is initialized to null, and the user field is also initialized to 0. Then here is the function, the class method function. So there's some mangling here, but it's in the module dconf, class A, function called foo. Takes one parameter, a hidden parameter, which is the dis pointer, right? The class itself. And all these things are just optimization remarks, right? No capture means it's not storing the pointer. Non-null means the pointer can never be null. Read none is it never going to read from this pointer either, because it's just going to return 0, as you see here. Okay. Then the virtual function call is here, happening inside this call foo function, where we first have to index into the A argument to get the V table. We load that V table. Then we index into the V table to get the method a.foo. Cast this method, because it's still a void pointer, we cast it to the actual function pointer, load that thing, and then call it here, tail call. This would be the indirect call. Multiply the result with 1, 2, 3, and return it. I'm going a bit fast here, you'll see more of this kind of stuff. But it's, I'm just trying to show you that I think it reads easier than assembly code. Kind of looks like C code in a way. Okay. In order to do this translation from D to LLVM IR, one thing that is extremely important is semantics of the D language, right? How do we, what is a D construct, what does it exactly mean, and how can we translate that into this LLVM IR language? And so clear and detailed definition of semantics is paramount for us. And very often I'm reading the spec to figure out what exactly is supposed to happen here. And unfortunately, the spec is incomplete on like very minute details that are important for us, and most of you guys don't really realize this, I think. And definitely Walter, he's raising his hand. For him, it's very important. Can you give him the microphone? For him, it's very important as well, of course.
I cannot emphasize highly enough when you say you run into problems of the spec where you can't proceed because of problems in the spec. Please, please, please put them in Bugzilla. I know people are getting really tired of me saying this, but it's really, really important because there's so many members in the D community who are always looking for something that they contribute, and even minor things like maybe tweaking wording in the spec is valuable. And like the previous speaker yesterday who ran into some problems porting DMD to a new platform, keep a log of all that stuff. Get it into Bugzilla. We can fix that stuff.
Yep, I couldn't agree more. And two things that I want to mention are if you have the language semantics, it's not necessarily what the CPU is doing. And two examples of this is if the spec talks about a function call, that doesn't mean there's a call instruction that the CPU is doing a call instruction, right? Because otherwise inlining would be impossible. The other thing is if the stack uses the word spec, if the spec uses the word stack, that doesn't mean that the CPU has to keep a stack of like popping and pushing of values on the actual stack, because some CPUs don't have this stack concept. They don't have special instructions for that. And also, it limits optimizations, and in fact, it will limit, later on in the talk, I'll show you, it limits also the capability of instrumenting your code. And again, so optimization and instrumentation heavily depend on these clear semantics being abstracted from what the machine is supposed to be doing, right? If you write a multiplication, that doesn't necessarily mean that the CPU has to do a multiplication, right? If the result is already known at compile time, you just use the result, right? There's no multiplication needed. Or if the CPU doesn't have a multiply operator, it would have to do something else, right? To make sure that the D language semantics are preserved. Okay. And then there's this other thing called immutable in the language that I'm not going to dwell on, also not in interest of time, but definitely this is something that I run into recently, and Andre already mentioned this, that there are some problems there in the spec as well. And we noticed this very clearly in when optimizing code. If you make use of the fact that something is immutable, your program will break, in fact, in strange ways. Okay. Now, the first more detailed topic that I want to discuss is profile-guided optimizations. And because I think it illustrates very well the optimization capabilities of LLVM, but also the instrumentation capabilities. And they go hand in hand in order to provide this particular functionality. PGO, who has used PGO? Okay, so not too many of you. As you've seen in John's talk, you should. It will improve your performance. Actually, first use LTO and then add on top of that the PGO. It's a two-step process where first you compile your program where instrumentation is added. So your extra instructions are added to the code that then at runtime emit a profile. So it stores a profile of how your program is running. And then in the second compilation step, you build the final executable using that profile data. So the optimization happens in the second step. The instrumentation happens in the first step. Make sense? And then, so the question is, what kind of optimizations can you do with a profile? And to figure out what information should this profile then contain, right? And one of the biggest optimizations that you can do is inline. Once you inline a function, this opens up the possibility of many new optimizations. For example, if you inline a function that takes a parameter, an argument, then after you've inlined it, you know the value of that argument, right? And so you can do some kind of compile time function evaluation, if you will, in the optimizer, purely because of inlining. So the inlining itself, eliding a call to a function, is not what makes it quick. What makes it quick is the optimizations that come after inlining, right? So what information do we need in order to make smart inlining decisions? Because inlining can also be bad for performance. And that's basically just control flow analysis, right? How often is this piece of code executed? Does it make sense to inline it at that point? If you have an if statement, if one branch is never taken, then don't inline anything in that branch, right? Just inline the stuff that's in the branch that is executed very often. And the other thing that is beneficial to profile is specific values during execution of your program. And specifically for indirect function calls, which I'll show an example of. Okay. Then what does LLVM provide us? LLVM provides kind of the tooling to do all of this, which is handling a profile file, writing it, merging it, loading it, viewing it. And it provides intrinsic functions to generate code that writes to that profile at runtime, and a runtime library that accompanies those intrinsics. And finally, of course, it provides us with the optimizations based on this profile, right? You tag instructions with the information you got from the profile, and the optimizer uses that information to generate better code. Now, what does LDC have to do? What we have to do is we have to add calls to these intrinsics that LLVM provides, right? We have to instrument our code ourselves, and I'll come back to that later. And then, So that's on the instrumentation phase, and in the optimization phase, we have to load the profile and calculate for control flow analysis from that profile and add that as metadata to the generated IR. Here an example of what it looks like for a very simple function. Function bar takes a Boolean 0, if 0, return 0, else returns a function call. Okay, something fairly trivial. What does it look like in the instrumentation phase? This is the IR. It's much bigger than you would expect for such a simple function maybe, but that's only due to instrumentation. Define function bar, okay. First thing that it does is these 3 instructions, which is loading a PGO counter. It's a function counter. How often is this function called? And so we load a piece of memory, add 1 to it, and then store that same value again. It's a counter of how often the function is called. Then this is the kind of the decode. We branch off on the value of the 0 argument, either to if or else. If the if statement, if 0 evaluates to true, we enter this branch here, and then again we increase a counter to test how often was this branch taken, and then we return 0. If 0 evaluated to false, we go to the else branch here, and we just call some function. Note that there's no counter at the else branch. Right? We could have added that, but in fact, to have your program run as fast as possible, we try to minimize the amount of counters we need. And this is the complexity in LDC. It's actually a lot of fun to work on, is how to, for this particular thing, there are only 2 branches, right? So it's quite easy. You know the input to start at the function, and we know the counter of 1 branch. So the total minus the 1 branch will be the counter of the second branch, right? Think of a switch statement, and then you suddenly need much more, and go-tos and other labels, breaks, continues, suddenly you need much more counters. But the same idea applies, where you can try to minimize the amount of counters, and then when you load the profile, you just calculate from this minimal set of counters that you have all the other values that you need. Indirect call promotion is related to not to control flow profiling, but to value profiling, where we basically try to store reoccurring values. If they reoccur very often, you can optimize based off of that. I've shown you a very simple example here. We have a function foo, return 0, and there's a function call indirect, which takes a function pointer, so it could be anything, and it calls the function and multiplies it with 1, 2, 3. Now if this function, so this is basically hard to optimize, right? We don't know what the function pointer could be anything. So we're done optimizing here, except that we could profile the value of this function pointer at runtime. And if we find that very often this function pointer is the function foo, what we could do is instead of calling the function pointer, we could check, is this function pointer pointing to foo? If yes, then take this branch where we can inline foo and optimize further. Otherwise, just call the function pointer. Make sense? Of course, and inlining foo here would be beneficial just because it's 0, and 0 times 1, 2, 3 is, you don't have to do the multiplication anymore.
Couldn't we upstream this optimization so that if you call indirect with a pointer that is at compile time known to be foo, it will actually call a different function?
If at compile time, if you would call indirect directly with the address of foo, the optimizer is smart enough to know, let's just inline this whole thing, and there won't be an indirect call. See what I mean? So it's more on the kind of unpredictable paths where you really don't know, and you cannot inline either at that point.
Just a very quick point on that. You can, if you want, do this yourself.
Yes.
If you, as the programmer, have information, or do suspect that foo may be called, and you're not using LVM but using DMD, which probably doesn't do this optimization, and if it does, it probably takes ages to run the optimizer, you can compare the function pointer yourself against foo and then call foo, and then the inliner can work on it.
Exactly, exactly, yeah. It's just work, right? Yeah. So, okay, what does it look like in LLVM IR? We first have to instrument our executable. And if we look at function call indirect, it's here in LLVM IR. First thing we do is, again, add the counter, right? This is this counting code for control flow. So increase the function call counter. Then we convert this pointer argument, this fpointer argument, we convert it to an integer, and to a 64-bit integer on this platform. And then we store that, we call an LLVM runtime function to store the value of this function pointer at that point in the program. And then we just call function pointer argument, multiply 1 to 3, and return. So the instrumentation, interesting thing is happening here is that we store the function pointer value at that location in the program, in a dedicated slot. Or in fact, actually what it's storing is the most likely candidate, or the most recurring candidates that it found at that location. So it will be a set of maybe 5 functions with counters next to them. Then the optimization, so we load that profile into the LDC again and generate this IR, where if we look at this call indirect function here, the first thing it does is it compares the function pointer with the address of foo, because it figured out while running this program, hey, foo is called very often. So it compares it and then branches off of the result of that comparison. And notice that there's this extra piece of metadata here, 29, so then we look here, 29, and it says branch weights. Apparently it was true 2,000 times and it was false 0 times. So it's very likely that the function indeed is foo, just the way I ran this program. Then here, if false, then do the original indirect call, right? So the branch was, the pointer is not equal to foo, so we really have to do the function call indirectly, multiply 1 to 3, and then branch to the endpoint of the function. If not, then we can inline the whole thing and we don't have to call foo. And there's a particular thing here, because LLVM is a single assignment language, you cannot, the value of one variable cannot depend on control flow, right? You cannot set it to one thing here and to something else over there. And the fine node here takes care of it. Basically, it says if the incoming branch here, so something branched to this label, if it came from this block here, then the value will be that. So that's the multiplication value here. If the incoming thing was from the first basic block, 0, then the value will be 0. Does this make sense? And basically there's no call to foo here anymore, right? There's just a comparison with foo, but there's no call to foo. Okay, more on this you can read about I wrote a blog post about it, also showing how you can do this optimization yourself for indirect functions and also for virtual functions, which is 2 lookups. John has a very nice presentation, I think, with also results on the interplay with PGO, with LTO. And then a final note, all of this that I've shown is done in this instrumentation, and the calculations are done in LDC. It's based on the DAST. A year after I made this, actually already while I was working on this, people in LLVM were working on something else, which is doing this stuff on the IR level. Right? So instead of us having to do it in LDC, it's like 10 lines of code, and LLVM does all of it for us. On the IR level, where you can do this PGO instrumentation kind of after some initial inlining, then do the profiling of this initial inline code, which can be more precise, depending on the kind of things you want to optimize, can work out better or not. Right now it doesn't work with LTO though, but I figured out what the problem is, and so hopefully we can fix that soon. Okay, something completely different, which is fuzzing. Who knows what fuzzing means? Okay, cool. So for those of you who don't know, fuzzing, at least what I mean with it here, is testing your program with a piece of random data very often. So you generate random data, you hand it over to your program, check whether it works, generate some other random data, check whether it works at a very high pace. And in order to kind of smoke test, to figure out where your program crashes or where severe bugs happen. It's not there to test the functionality of your program, right? You usually don't test whether the program generates correct data from that random data. It's much more of a, if you receive untrusted data from someone, you don't want that guy be able to hack your system by crashing it in a way, right? That's the kind of testing that I'm talking about. But of course, generating random data doesn't mean you'll find the bug very easily. And let's look at this function here. So we have a function called FuzzMe. It takes an array of bytes, and then what it does, it tests whether the first and the nth element are less than, greater than, and that the two chars in the middle are equal. Some bogus function I wrote yesterday evening. I set n to 10. I test whether the array is size n or larger. Then I check whether the first element is this less than. I check whether the characters in the middle are equal, and I check whether the last character is greater than. If so, I return 1, otherwise I return 0. Who sees the bug? Okay, 2 of you, 3 of you. There's a severe bug here. And in fact, we are saved by these safety, or these array bounds checking. Data n, this one will be out of bounds, right? Because the array is of length n, meaning that we index from 0, so the last element really is n minus 1, right? If you throw random data at this, it will take quite a while, right? Because we have 10 bytes, so we have 2 to the power 80 of possibilities, right? And if we start from like 1 byte and try all the possibilities, and then 2 bytes, try all the possibilities, 3 bytes, it will take a very long time before you find a bug here, right? Also, if you immediately generate a 100-byte array, then maybe the first check here will fail. It's not going to be a less than sign, right? So then the actual bad access will never happen. Same with this intermediate check, right? These two characters have to be the same. So then still the crash won't happen, right? So a lot of things have to match up before the crash actually happens, right? So if you just throw random data at it, it will take a while. So you have to do something smarter, and the smarter thing is what LLVM can do for us. It can instrument the executable by measuring or instrumenting these kind of checks and looking at how the control flow of the program changes while generating new random data. Right? And so it basically figures out which bytes are interesting in this random data set and which modifications don't lead to something new and which do lead to some new control flow paths checking. It's like looks at coverage, if you want. It's like a coverage checking. So let's see if I can quickly. Can you read this? To test this, all you need to add is 2 lines of code. So we have this FuzzMe function that I just showed. The 2 extra lines I have to add is import ldc.libfuzzer. And the second line is this one, mix in define test1 input, and as a template parameter, you pass the name of the function that you want to test. That's it. No main is needed. Main is provided by the fuzzer library, and all you have to do is tell it which function to test, which is what I do here. Okay? Now, if we compile this, okay, it's here. So we compile it with LDC, we turn on the fuzzer, fsanitize equals fuzzer, compile it, go, and then we run this executable. And bam, it happens really fast. What it does, it starts to throw random data at it, and as we scroll up here, it outputs some information and then starts to throw random data at it and discovers new control paths taken. And here, another new control path was taken, something else, and then, oops, bam, hits range error, range violation on line 16. This is this bad access that we do on the array, right? It outputs the stack trace, and the best thing it does is it outputs the test case for which it broke, which you can find over here. I hope you can read it, but in the end, what it shows is, the first element has to be this less than sign, somewhere in the middle they have to be the same, and the whole thing has to be longer than 10. Or actually has to be length 10 exactly, right? If it would be longer, there would not be a bad access. So this was much faster, I think, than doing the real random testing, or like starting from 0, 1, 2, 3, 4, 5, 6, right? And I didn't have to tell it anything about my program either. Right? It doesn't know anything about it, really. Well, due to instrumentation, it does, but...
In your example there, it looks like you've ripped out your function and put it in a special compilation module. Is there any way to do it while it's in, like, let's say you want to fuzz test a function that's actually in your project instead of having to rip it out and put all the...
Okay, yeah, it's a good question. So what you have to do, indeed, is to write a separate program with a FuzzTarget, is what it's called. So this FuzzMe is what you would call a FuzzTarget, which would call something from your program, so as a library. Yeah. To get fuzzing going. For something the AddressSanitizer thing, you can do that on your own program, but I'll show it later. Okay.
So I found this kind of fuzzing very useful when you write like a parser or something, which is very constrained and has a somewhat limited set of like possibilities or branches it can take. But anything bigger, let's say a compiler, like just doesn't get anywhere anytime fast.
Yeah. Okay. So this is at the moment still generating random data. We don't give it anything. And if your program is more complex, like if you want to fuzz the D compiler, where the D language is more complex than just random data, it may take a lot of time to reach the deeper parts of your program, right? You can give it a library of keywords, for example, so that instead of completely randomly generating data, it generates somewhat more data that makes a bit more sense for your program, and the whole thing goes deeper. Also, what you can do is run this forever, right? You can just keep it running and build a corpus of test cases to reach deeper parts of your program, and then combine those for more random data. Yeah.
American Fuzzy Lop actually takes in binary data that's supposed to be normal data to your program, and then fuzzes that. So
Yes,
that
yeah.
already.
It's the same here. Yeah, so you can do the same here.
Okay.
Yeah.
So you
could
can give
do
it binary data for it to start with?
Yes. Yeah,
Oh,
yeah.
okay.
You can give it a corpus, yeah.
All right.
So we just had done a lot of very successful cases of fuzzing for the Scala compiler, so you can definitely fuzz input for compilers.
Yeah.
And basically, the two different approaches with both work. One takes existing test cases and just fuzzes them. And the other uses essentially recurrent neural networks with some fancy function to essentially build programs according to the grammar, and again with fuzzes, so with some incorrectness there, and you can tune it, and both work great and both cover different test cases, I found.
Yeah, thank you for, exactly. In LLVM they do the same, it's indeed, it makes sense if you want to test the deeper parts of your program to make something that generates stuff that looks like real code, right? You have to be smarter about the randomization. Yeah. But the main principle stays the same. What does it look like in LLVM IR? I have to go quickly. Let's look at the FuzzMe target when it's instrumented. The FuzzMe function, there's a lot of code here that is basically what LDC would generate without instrumentation. Right? So there's already branching going on. Lots of labels here, just because we do this if statement, and then this, and then this, and then this, right? If you instrument it, it looks even more complex, but I just want to show you the kind of the essence of it, where what is added are a lot of calls to these sanitizer runtime functions. For example, here, there's a call sanitizer coverage trace const compare 8. So apparently it kind of, here it instruments the first comparison that it's doing. And it checks then whether this comparison, what value was it checked with, but also was it true or false, right? How did it came out? And that's this thing here, where it traces the program counter in this particular part of the program. Later on you can see, aha, here there's another comparison. Now it's on a Boolean value. And all of this is used for the fuzzer to measure what is my program doing, kind of profiling your program as it's executing the fuzzing or throwing random data at it. Now, what is nice in the fuzzing is actually was developed for C, I think, or like LLVM mostly works with Clang, or that's the primary development target. But C++ doesn't have array bounds checking, or you can if you use .add for vector, right? In any case, in D we have this, right? So we get for free the extra checking on bad memory accesses. However, if you do pointer math, or if you work in release mode, which you shouldn't for this fuzz testing, but let's say you do, you've intentionally disabled array bounds checking, there will not be a crash happening, right? The fuzzer it will throw random data and the program will not fail, right? So it won't find the bug. Now what you can do is just add extra sanitized checks on your runtime code by passing a flag to the compiler just to add extra instrumentation. It's very similar to the array bounds checking, but a bit more powerful. One of the things that I find is most powerful, at least at the moment, is AddressSanitizer, which is a memory access bounds checker. It basically stores at runtime which parts of memory are valid to access for your program and which aren't. And once you access invalid memory or a poisoned memory location, it just errors out. For example, for an array bounds check would be, the array itself would of course be valid, but already the value immediately after it would be invalid, and that's how you can check that thing.
Yeah, as an example of this, in the garbage collector, there used to be, I'm not sure if there is there anymore, but to add these guards to each memory block, so for the same, if you write or if you read, it will crash.
Yeah, I've seen it, yeah. So the D, it's disabled for now. In fact, actually the D garbage collector at the moment means that AddressSanitizer doesn't work too well, because what the garbage collector does is it first allocates a large pool of memory using malloc, and AddressSanitizer knows how to deal with malloc. If you malloc something, it adds before and afterwards, it adds this flagged region. But if you allocate a large pool of memory and then give the user memory inside that pool, the whole pool will be marked as valid memory, right? So in order for this to work well, we have to modify the D runtime basically to work with AddressSanitizer. And I'm working on it, it's not finished yet. It's just I wanted to mention this because even if you write at system code and you do also kinds of pointer math and you work with malloced memory, then AddressSanitizer will work very well. And I have been able to find at least one DMD bug, a parser bug with it, where it did a memory overread because it was working on mallocked data, basically. I mentioned something about the stack, and that the spec shouldn't be specking that the stack has to be the stack with the push-pop thing. And that comes into play when using AddressSanitizer. You can tell the LLVM optimizer / machine code generator that, hey, we want to use what's called safe stack, meaning that we don't want to do push and pops on a stack. No, every local variable, just allocate them on the heap. Just allocate everything on the heap and put flags around it. Other ways of thinking about it is that you can already do that if it's on the stack, right? So the AddressSanitizer by default will put red zones around values on the stack, but then you cannot detect stack use after you've returned from a function. Right? If you access a function's local variable after you've returned from that function. If you allocate it on the heap, you can, after the function returns, just flag that whole piece of the heap as invalid. Make sense? But for that to work, the language semantics of D have to not assume there to be a stack, right? So that you can randomly put the whole stack anywhere in memory. And D does this already, so you don't have to worry about it, which means this will work. And if you can read very quickly, there's a function here called make A. It should return a class A, but it's allocated on the stack here using scope A. And then we return that thing, and then we access a function of it. And so clearly here we access something, a variable that is located, or is a local variable to the function, but we've returned from the function already, right? So it's a bug. This was taken from the forums, by the way. And this won't crash your program. It will work. So there's kind of a latent bug here, right? Normal execution will not find this problem. But we can compile the code using AddressSanitizer. Note, I've put AddressSanitizer here. And then run it. Hey, nothing happens. That's because I didn't enable the stack relocation mechanism, right? If I do, there we go. Now, immediately the program crashes and AddressSanitizer reports stack use after return on address blah blah. And there's a lot of information for you to figure out where exactly the bad access happens. In the interest of time, I have to go to my last few slides. You can read more about LibFuzzer online and AddressSanitizer. Documentation is very good for these two pieces of programs. Now, the next speaker is laughing, good. He made a library called DXML, which is a library that takes user data, which may not be, it's kind of untrusted, and parses that piece of information. So now I leave it up to, okay, what shall we fuzz it? The news is positive, I can tell you. Okay, who thinks the program is going to crash? The news is positive, though. The news is positive. Okay, so I wrote a FuzzTarget yesterday evening. It's 5 minutes work, right? It's really easy to write this, and I wanted to show it on a real project. So if you forgive me the extra time. So we make a FuzzTarget. It takes this data. I import the DXML parser, and I pass that data immediately to parse XML. Then I do some extra stuff to make sure that the optimizer is not going to elide it, right? I have to use this data. If I'm correct, the parse XML function can throw an exception, which is good, because then it reports to the user, you did something wrong. And that exception is XML parsing exception. In all other cases, this should just work, right? It shouldn't crash your program. So let's see how quick it finds something. Might take quite a while, right? Because I'm not passing it anything. So this is an XML parser, but I'm not giving it any dictionary, no corpus, just random. So now let's see where I have it. Fuzz XML. Okay. Run this, please. So I compiled it here with I hope you can see it. I compiled it with the fuzzer. And let's start the program. Okay. What you see here is that oh. The news is positive, though. Please hang on. So what it did is it threw random data at it, and as you can see, it found each line is a new control flow path that it found, and it can store all these things in a corpus of like, hey, that's an interesting test case because it covered a new piece of code, right? Unfortunately, though, at some point, very quickly, it crashed the program somehow. But it's not so bad. Jonathan knows about this because he. Well, so it actually hits an assert, which I don't think is nice for the user to have happened. But it says assert, and its name cannot be called with text. So there's of course, this is super malformed XML, right? It doesn't look like anything like XML at this point. But it hits an assert. And if you run it again, it will hit another assert, which I think is positive news for the library. I wasn't able to crash it in a way that Jonathan is not aware of, right? It hits an assert. And basically, what I have a test case for you. I can just send it to you. It's a file. You know, if I parse this, you hit this assert, so you have your test case ready. And then to conclude, maybe a small summary. So, first thing, generally, if you want to learn more about compilers, especially the low-level parts of it, machine code and optimization, read LLVM's mailing list. It's a very interesting technical crowd, very knowledgeable. If you want your code to run fast, use PGO. Better use LTO. Let's see. Use LTO and then incorporate it with PGO. If you want your code to run safely, start fuzzing your code and use AddressSanitizer. There's Google has a OSS fuzz project where they basically provide you a server that is continually fuzzing day and night on your open source project. We should use that. If you're interested in working on LDC, there was a presentation yesterday of kind of motivating people to work on a compiler. And then the presentation afterwards, someone showed, if zero, that you can optimize that. Well, actually, we've had, since half a year, I think, we have an outstanding good first issue on GitHub to do that optimization. It's not trivial, by the way. And if you want to join me in working on aggressive optimizations, let's add these nitty-gritty details to the spec. Right? As Walter said, put in bug reports. Thank you.
All right. All right, thanks a lot, Johan. We're not going to have time for questions. Let's go ahead and take a short break. Please be back here by 10 after, and we'll hear about something I think everybody's interested in hearing about. All right.